All right, we should be ready to begin here, so hopefully your day is going well. We're going to begin this module with a bit of a vector introduction. Students and even myself often have trouble understanding what a vector is, and sometimes they use the term vector is used for different things, such as the disease vector. There's also the vector library in C++. So the term that we're working with when we're thinking about a vector is a 2D vector, which means that it's a point or a direction that's represented in 2D space. So 2D space meaning just X and Y coordinates. That's kind of done with the coordinate system of the screen that you're working with, and all 2D programming games work with that coordinate system, and that means that your X increases as you go to the right, your Y increases as you go down. The origin of your coordinates is 0, 0 in the upper left-hand corner. We're also going to implement some basic collision detection of a template that I've provided for you to bounce off the edges of the screen. So we want to take a moving item and detect when it moves off the screen and bounce it back. So that actually is collision detection that you can use to meet your project requirements. That is collision detection. So I'm not really, as far as collision detection between two moving items. We're gonna talk about it, but it gets so intense and as far as prerequisites and pre-knowledge that we're not going to get too deep because we can't. We would actually have to be required to have some special mathematical prerequisites. But I'm still going to show them to you and give you the tools to work with it if you so wish. So let's go ahead and talk about vectors real quick. I got a PowerPoint to go through and kind of the introduction of an object library that we're going to be using in our templates. And then I've got an example from the previous module where I give you an example of the drag and drop, but I talked about an example of being able to do with the mouse, sort of like on those pool games that you may have played, where you hold down your mouse and drag back on the pool stick and release, and it. I call it the drag and release example, and what it does is it allows you to drag and release an object. And the vector that you're using or the angle of the release is the direction that the object will travel in. However, we're going to just use it as an example, and then of course get some simple collision detection done as part of it. So let's go ahead and start talking about vectors and what a vector is. Let me make sure that my audio is working here. I think it is. All right, so we're doing well. All right, so a vector is two different things. It's essentially something that describes a location, and also something that describes a direction. So you can read about this a bit in one of the books that I have you work with. The introduction is worthless. Don't even worry about reading that. Just go right to vectors. Now, as you're learning about vectors in here, he uses a special bit of or a special platform for processing that you can actually use alongside here, but it's not JavaScript. It's very close to JavaScript. I think it's called a processing something or another. You can use that platform if you wish as you're learning about this. Basically, it's a dumbed down JavaScript program that you can download and use. But as far as the straight up knowledge of what a vector is and does, You can read through these, and then we're going to be applying these concepts in our own code as we progress. And of course, I provided templates for you so that you don't have to spend time on stuff that we've already learned, obviously, and of course, easily put this new knowledge into use. So let's start with just the simple introduction of vectors, and this is just the intro. We're going to be talking about vectors. You got a whole assignment on vectors. So if you don't get through all of the vector reading here, next week you're going to be doing the same reading. Or the next module. This is meant to be an introduction to get you ready to delve into vectors, so go ahead and start your reading. And of course, Google it. Start learning about 2D vectors. There's a lot of stuff out there that doesn't help much, unfortunately, but hopefully we will get through that over the course of our videos. So let's go ahead and look at the two parts of a vector, and we're going to start with just a PowerPoint, and I'm going to talk about vectors with code. So the PowerPoint that I have available for you for this week is here. So when we think about a vector, the idea of a vector, you need to kind of think about a vector, but also keep in mind your frames. Because a vector is a location, yes, but it's also describing movement for each frame or each run of the loop, of your game loop. So often we refer to it as change of x, change of y, or delta x, delta y. And that is the change, how much your x position changes each frame, or how much your y position changes each frame. So the part of a vector that is a location and also a direction is simplified down to two numbers, x and y. So when we think about a vector, we can use it for the location or the change of x or the change of y. So it can be both x and the change of x, or the x and the change of y. So the vector is used two ways, location or direction. So the library for a vector is fairly simple. All we need to do is have an x and y in it, and then we use that x and y depending on how we write the code. We use the x and y value as a location, or we use it to describe a movement or a change of an x and y value. So let's look at that. I've got a whiteboard. Hopefully this will work out all right. We'll see. Let's start with a location vector. Okay, so our location vector, I'm just going to label with an R. Let's say that it is 10 by 10. So that would put it roughly, and let's say that each of these squares is more than one. But for our purpose, let's say that kind of puts it right about here. Okay, so that's our location vector. And it's static. It doesn't move. So its x is 10 and its y is 10. And it's located right there. Now let's talk about a position vector. Now let's say that is this position, or not position, but a direction vector. Let's say that this direction vector, and let's actually label that D for direction vector. Let's say that is 1, 2. Okay, so if we have a vector that's located at position 10, and we say that we want this vector, this location vector, to change by 1, 2 every frame, then that means its new position, the new position will be 11, 12. You always add a direction vector. You could also subtract it, but that would be senseless, because what you could do is a position vector does not have to be positive. it can be negative. So that's why a vector, you never subtract a direction vector. You always add it. And if you want it to go backwards, you just put the negative sign right here. And it'll reduce the value. So you always add a direction vector to a location vector. Now, if we were to make this -1, 2, then the new vector would be take their location vector, add the direction vector. 10 plus a -1 is a 9. And then 12. Okay, so that describes how you take a location vector and a direction vector and combine them. So you always add the direction vector, and you never subtract a direction vector. However, your direction vector can have a subtraction in it as far as describing movement. Now, if you have a -1 here, this is the x position. That means that your direction vector is describing a negative value. So let's say that every frame we are going to change this back to positive. So let's just say 1, 2. 1, 2. I start my location at 10, 10. So that means that my frame, or every frame, the direction of my location vector is going to change by 1 pixel and to the right for the x position, 2 pixels down for the y position. So the next frame, this is going to find itself 1 over and 2 down. So this no longer, when the next frame happens, this moves down to here. Because what we did is we added the location vector, or the direction vector, to the location vector. Now the next frame comes around, and our new value of our item is 11, 12, but the next frame comes around and we add another 1, 2 to that. So we add another 1, 2 to that. So now it becomes 10, or 12, evidently I can't do math this morning. It becomes 13, 14. That's this next new vector. So now this new vector goes out 1 again and down 2, and it's now here. So you can see that every frame, every slice of each frame, you're moving by 1 across and 2 down, 1 across and 2 down. And you add this direction vector to the location of an object, each frame, and every frame you can kind of think of as a slice of time. It moves that much. Okay, so it's going to continue to go in that same slope, 1 over 2, or 1, 2. So let's say that you change. Let's say that we start with a direction vector, or let's say that we start with another vector. And let's say that the vector is, I don't know, let's say that's 50 by 50. And let's say that puts us right here about. Okay, and now let's say that our direction vector is going to be a negative 0.1. And the negative 0.2. Okay, so that's a -1 and negative 0.2, evidently. So what that means is that every frame that you're going to be moving, you're going to be going and changing the location vector, adding -1 and negative 0.2 to it. So this position is going to go -0.1, negative 0.2. It's going to follow a slope that's like this. Oh, whoops. Actually, you know what? Let's just restart. Okay. So let's go ahead and I'm going to pause it real quick, and I'm going to get, we're going to restart our vector discussion, and we're going to talk about another part of vectors that you have to be aware of. So I'll get some drawings up and come back. Okay, so here's the other aspect of vectors to understand, is that when we're using a vector to describe direction, if we use a number less than 1, our direction goes outside of the integral values of the x and y coordinates. So that means that even though we can only draw with integers for a vector position, we can use a direction vector to slow down an object so that it doesn't move between frames. But it does move after maybe 10 to 20 frames, depending on how long it takes to add that direction vector up to a single integral value. So our direction vector is now 0.1, negative 0.1, and negative 0.2. So that means that to become 1, 2, it has to be added up 10 times. So that means 10 frames would go by before that actually shows its movement from one pixel to the next, because it takes 0.1 times 10 to get to 1. And since our x and y is integral only, it takes a while to have that movement be realized on the screen. And we want that actually because our direction movements and everything that we're doing has to be floating point based on just pure physics. And it actually makes everything smoother and flow better regardless of our mathematics. When we actually go to draw to the screen, we're literally working with integral values only, no floating points. So all your floating points will be converted to integral values for an x and y position. However, we can use a floating point to describe the movement, but it only manifests after that movement has added up enough to show on the screen. Let me kind of demonstrate. So if we have a location of 10, 10, now let's say we have a direction vector d2 of 1, 2. Okay, so that means that this guy with d2, within one frame, it's going to move over and down to here. So after one frame, it's now going to be located here. And that's after one frame. Now, if we use a direction vector such as d of negative 1, negative 0.1, and negative 0.2, notice it's the same slope. So it's going in the same slope, but in backwards. So it's going negative 0.1, it's going to the left every frame, and it's going up by 2 every frame. But it's only doing it by 0.1 and 0.2. So that means after the first frame, it's going to be right here. Then the next frame comes in, it's going to be there. Then the next frame, and the next frame, and the next frame, until it gets to the 1, 2, and it'll be 10 frames before it's drawn and the movement becomes real. So when you're thinking about vector direction or movement, there's a lot to it. Especially within the physics of your game. If I am describing a direction of 1, 2, that means that for every frame, then that means that that's something that's moving relatively quickly versus negative 0.1, negative 0.2. Or how about D3? 0.1, 0.2. So D3 is going in the same direction with this slope. Whoops. I wonder if I can undo that. Control Z is the guy's best friend. There we go. Okay, so D3 is -1, 2, or 0.1, 0.2. It's going to move very slowly and take 10 frames. For some reason, my pen is just a little turd here. All right, the heck with it. So this D3, 0.1, 0.2 is going in the same direction as 1, 2. It's just going slower. So D2 comes down to here in 1 frame, but D3 is going to take and do 0.1, 0.2, 0.1, 0.2, 0.1, 0.2, 0.1, 0.2, until it gets there. So it's actually going in the same slope. So 1, 2 is going in the same direction as 0.1 and 0.2. However, this one is slower. It takes 10 frames to get up to that 1, 2 change. And that's kind of the main thing with vectors that you got to understand is, direction, but a direction vector has more parts to it. You can take a direction vector and slow it down. So essentially, if you have a vector of, let's say, Control Z again. I wonder whether this thing is being a stink. Okay. Yes. Okay. All right. I think I just need to hit the right. Okay. So let's say that we have a direction vector of, let's say, 3, 6. So 3, 6 is going in the same direction as 1, 3. Because if you take 3 divided by 3, you get 1. 6 divided by 3, you get 3. So that means that if you have a movement of 3, 6, let's say your starting location is here, you go over 1, 2, 3, you go down 6, 1, 2, 3, 4, 5, 6. So in one frame, your object for a direction vector of 3, 6 moves from here down to here. Or the direction vector 1, 3. So you would go 1, 1, 2, 3. It would move here instead with 1, 3. But you see how it's going in the same direction as this guy? So a lot of times what you'll find is they will actually take and reduce a vector down to its smallest part. And that smallest value is a value between 0 and 1. So essentially, if you wanted to reduce 3, 6 and 1, 3 down to its smallest component, you would come out for both 3, 6, if you divide it by the same number, you would come down to its most common denominator, which is, I think I'm using that term right, which is 0.1 and 0.3. So these directions could both be expressed with a value that must be between 0 and 1. And 3, 6 would be coming down to 0.1 and 0.3. 1, 3 comes down to 0.1 and 0.3. And this is called normalization. So a direction vector, you could reduce the value, or the magnitude is the term, of a vector to have a smaller vector that describes the same direction. And then once you know the direction of a vector, you can increase the magnitude or decrease it as much as you want. And that's kind of the big idea of vectors, is we're not always really worried about the movement. We're more worried about the direction of the movement. Because if we have the direction, we can do whatever we want with speed. So this is a direction that has less speed than this one, because it takes 10 frames to get this direction to 1, 2. And then you can also have your other directions that go with negative values. Okay, so let's look at the PowerPoints. I'm going to be covering this again. We're going to be talking about all this stuff some more. But one thing that I want you to have an understanding of for this particular portion of the course is what's in our objectives. So our objectives is to describe a 2D vector. Okay, so remember, a 2D vector describes an x and y position, a location of an object, or it describes the direction that the object moves in based on a single point in time. And that's where your frames come in. That's your measurement of time. So you're going to be moving objects each frame based on their direction vector. And the magnitude of that direction vector, how big or how many pixels it moves per frame, describes the speed of that object. So describe how a vector behaves with a game loop. That's what I just described that to you. So essentially, the game loop is your time. It's your frames. Define two main uses of a vector: location and direction. Okay, so implement a simple collision detection on screen H. Oh, now we get to have some fun. We're done with the goodies, or the baddies. Now we get to the goodies. Let's go have some fun. I gave you a really awesome template that you can use as an example for the kind of drag back and release behavior that you get for the games in like a pool game. So what you're going to do is you're going to go to modules, and you're going to download the example template. Now this is where I start making the change to where I'm no longer going to be building projects from scratch. We're going to be all going from templates. I think we have enough experience, as though that we took the templates and changed nothing, and pretty much just copied the code over. So now you should have a pretty good understanding of the infrastructure, and nothing's really a mystery as far as the way things are working together. And that's the whole goal of this first couple of weeks, is that you understand how things work together and able to actually program in your infrastructure and your environment. And I think we've been successful. So let's continue, and let's go with this little bit of a fun template that I have. And it's going to be kind of a continuance of the mouse chapter, which is what I wanted this project checkpoint to be, kind of like an in-between between mouse and vectors. So to prepare you for vectors and also to finish up the mouse stuff. Now we're not going to talk about the mouse stuff today. We're just going to be doing the bounce around the edges code. And I probably have the code already down here somewhere for you to download and work with. So I think I grabbed a template, but we're going to do the code one piece at a time and explain it as we progress. So the code that you're going to be using is this one in the project checkpoint and vector introduction. It's going to be this module 6 template _stu. So you're going to grab that, and you're going to download it and zip it out, or unzip it, and you're going to have it on your desktop, and you're going to, here it is right here. This is module 6 template stu. Let's just run it, and then we're going to open it up in NetBeans. Let me just kind of show you what it is. There's a little bit of some higher level stuff here that I added just for your pleasure, because we're going to just be adding a simple portion to it. Now, if you do the mouse click down, hold the mouse down, and drag back and release, what it does is it moves in the direction of how you drag back. And so there's a lot of vector math that goes on in this, because I also add the speed based on how far you drag back, the faster it is. It's kind of cool, really. There's code in here that you won't understand. Don't worry about that. We're going to just work with some other code. What we want to do is we want to make this object bounce off the screen. And right now what it does is it just kind of goes around the world. So if I sling it over here, it goes that direction. And what it does is it just detects when it hits an edge, and then it just changes the position of the object. So let's look at this code, and what we're going to do is we're going to modify it so that instead of just going and moving it back to the left side here, we want to make it bounce off the edge. And again, so this is code that you're probably going to use in the future. And also you can use it as one of your requirements for collision detection. This one is actually performing collision detection. It detects that we have gone off the screen, and to reset the location of the object off the screen to the other side or to the left so it can come back into view. So I call this around the world. And it works in both up-down directions. Okay, so the detection's already there for us to work with. We just got to change the code a little bit. And also, it's kind of cool. It's fun to play with. So that's another reason why I built it. It's a nice little project break area. So let's go ahead and open this up and have a little bit of fun, and then I'll release you to continue with your endeavors. We got PowerPoints we got to cover first. Oh boy, I just got all excited. Well, let's at least get it in NetBeans, and then let's talk about the PowerPoint. And it's going to be quick because we're going to be doing this again next week. Okay, so let's go ahead and load that module in. Okay, it's module 6 template _stu. Okay, so we have this, and we're going to go over the code, but the main thing here that's changed, we have our tools, our sprite, our mouse manager, our key manager, our game, and our index. So nothing's changed here except for adding this math vector code. Now this is actually a class that I've put in here, and there's a few issues that need to be fixed on it. One of them is oh no, this one's okay. So this is a class, and there's actually two classes in here. One that I don't use is this function point that I don't use. But and this is the point object. So you could actually put a point object in here, but I just said the heck with it. Let's just put our x and y into the vector itself. So you could actually just get rid of this. That can go away. So here is our vector object. And it starts with the vector declaration, and when you instantiate a vector, you send the x and y values to it. Now I put the pi value in here so it has greater it has a higher level of precision compared to the math.pi value available in most libraries. And that's not really something that's needed. You can ignore that and get rid of it. Doesn't need to actually be there. So that just reduces it down to these components, which is math vector, or this.x and this.y. So that's actually in our PowerPoints. So this is our object. It just literally contains an x and y value. Now what we're going to want to do is we're going to want to be able to, well, I just lost my train of thought. Let's go ahead and continue with the PowerPoints. Okay, so this is a little bit on the nature of code describing direction between point A and B. We already described that. So we actually already covered this too. So here we go. This is the vector implementation. So this is for your sprite. You can implement a vector for your sprite instead of X and Y. And that's where you come in with some other things for your sprite, because now you need 3 values to work with the movement of an object within 2D space using vectors. You need to have the original vector, which is the location of the object, the velocity, which is the change of X and Y for every frame, and then the acceleration, which is the change of the velocity, which is the change of X and Y, which changes the location. So acceleration changes velocity, that changes location. We're going to be covering that more. But those are the 3 things that you need to describe a moving object in any space, 2D or 3D. And then, of course, we have sprite width and height, source image, source width, all that stuff. So that's how you would implement your sprite with or your how you would implement a vector with a sprite vector. And I believe I actually show that and demonstrate that in the template. So let me go ahead and verify that. If we go here to the template, we go to sprite. Yes, I did implement this sprite with location, velocity, and acceleration. So this is the stuff that you're going to be learning about. And then also we have to take into consideration our speed changes when we're working with a keyboard. We do it essentially I do it as a component of the frames per second. And that helps bring things within a standard threshold as far as speed is related. So remember, you change the acceleration, and the acceleration changes the velocity, which then changes the location, and then your redraw right here will have the new values for the location. So when you're working with vectors for 2D, you first change the acceleration, which changes the velocity, and then the location. And we do that through all add functions. Now, for this purpose, the thing that we are working with is this check edges function. Now, in the sprite update for our template, this is our sprite update. Now, in our game, we create the sprite right here, just like we did for our hero code. And then in the game, we tell the sprite, which is a ball, we call the sprite the ball, we tell it to update. And we send it the key state and the frames per second. And that ball, which is our sprite, then runs this update function. And what it does is it looks at the key state and sees if it needs to change any directions. And I believe that I made this project so that you could move the ball if you wish with your keys. Which is keyboard input right there. And it's pretty slick, man. It works really good. Or you can drag it and release it. So this is kind of I'm showing off a bit, okay? I'm going to put it that way. This is what you're going to be learning about how to do other than the mouse stuff. The mouse thing is just actually showing off. This stuff we're going to be learning about. So what we want to do is we want to work with this check edges function. What this check edges function does is it looks at the sprite and its environment, and what it does is it looks to see if the sprite's next to the screen edge. So with this check edges function, what it does is it looks at the location of the sprite, and it compares that with the canvas width, the width of your screen, and the width of your sprite. Because if you are looking to detect your edge of a sprite, there's a few things you got to keep in mind. And let's talk about that real quick. Okay, so your sprite is a box. Now here's the problem with this box. Its location is always in the top left-hand corner. That's the location X and the location Y. So to detect when this sprite goes off the screen, goes next to the edge, you've got to actually be looking here. And that's why you add the width. So that's why when you're looking at an edge, you take the location of the sprite, which is here, you add the width, and you make sure that that value together is not greater than the width of the screen. And if those two values, the location of the sprite added to the width, is less than the screen width, then you're not at the edge. However, let's say here, let's say our sprite's right here. Now let's say that the screen width is 800, which is a common value. And our sprite is 50 pixels wide. And our location is at 780, our X location. So that means that we take X 780, that is location X, that's this guy right here, location X, 780, plus the width. Or, excuse me, you say that the location.x, if it's greater than the width plus this dot width. Okay, so what are we actually looking at here? Oh, let's do the math on this. If location.x is greater than the canvas width plus this dot width. Oh, I do the plus 50 on that. You could do plus 50 here plus this dot width. You could do it one or the other way. But essentially what you do is you take the canvas width, add it to the width of your sprite, which is going to be, from what we got here, the canvas width is going to be 800 plus 50, which is the width of the sprite, so it's going to be 850. As soon as this sprite or this location gets beyond, it looks like I'm working with, I'm allowing it to roll off screen so that we don't reset it back to here until it totally goes off screen. So if we want to do a check edges bounce, we've got to do it so that we locate when this position gets right there. So this is a round the world algorithm that we're looking at. We want a bounce edges. So let's actually start developing that so I can talk in terms of the bounce edges instead of the around the world algorithm. And we're going to actually use the initial portion of that code to make this bounce edges work. And we're going to come back to this. So let's go ahead and go back to the code and make a few changes and actually implement that check edges, and then I'll explain how it works as we progress. Okay, so here we go. Check edges. Oh, Cool. Bounce edges is already done. Wow, your homework is easy this week. All right. So the sprite, the bounce edges of the sprite needs to be called, and then we're going to talk about that. So let's go up here to the input of the sprite. Now remember, I'm in sprite.js, and instead of check edges, you're going to hit bounce edges. Okay, so let's do a save all and look at how that and work on and look at how that works, and then I'm going to explain it in the drawing window. Okay. Okay, so instead of check edges, we're doing bounce edges. Now you see there's a bug there. It's not working very good. Now that's because you actually need to add the velocity of that. So let's go ahead and play with this and get it so that it'll work properly instead of just getting stuck there. Let's see if we can fix it. But first, let's talk about it. Because obviously something's changed here. So we're not going to do the check edges anymore. We're going to do the bounce edges. All right, so here we go. If location.x is greater than canvas width minus this dot width. Okay, so let's talk about that guy. Go back here to the right board. Control Z, clear canvas. Okay, so our little moving ball, let's say, is right here. This is actually going to be beyond our detection. We should be detecting it right here, but I'm going to give this as an example. So let's say that the width is 800. That's the canvas width. Canvas width is 100. Sprite is 50. The location, so this is 50 pixels, is 50 pixels wide. The sprite location is going to be 780. Okay, we'll want to detect that this guy has hit the edge. So that means we got to take the 780 and we've got to take into consideration the width of the sprite. Because our X location 780 is right here on the upper left-hand corner. So in our algorithm, we got to look at the width. So what we say is if this dot location (780) is greater than canvas width, which is 800, minus the sprite width, which is 50. Okay, so is 780 greater than 800 minus 50? 800 minus 50 is 750. So yeah, it is. So that means that with this math, we've detected that we've gone off the screen. So 780, 800 minus 50, size of the screen minus the width of the sprite, this guy, is going to be greater than 780. And you can do this math you can do this another way. You can take 780 plus 50 is greater than 800. So you could actually do it this way. This location, we can do 780 plus 50 is greater than 800. 780 plus 50 is greater than 800. That makes a little bit more sense to kind of visualize. So that means that we are saying, hey, is the location plus the width of the sprite, this guy right here, greater than the width of the screen? And sure enough, 780 plus 50 puts us greater than 800. 780 plus the 50 of the sprite. So we've detected, hey, oops, this needs to bounce. So that means that there's a problem here. We want to bounce that. And what we do is, since we're using acceleration as our direction vector, what we're doing is we're going to say, hey, reverse your direction. So let's say that my acceleration is, my direction vector for this guy is negative, or is, excuse me, it would be 1, 2. Say it's going say it's moving this way, and it hits the edge right here. What I can do is I can just multiply each of these by -1 and change the velocity or the direction vector so that now it moves -1 minus 2, and it starts going and it bounces off the screen in that direction. So let's go back to here. Let's Control Z. Oops. Okay. We can do plus this dot width here. Doesn't matter. It's the same thing, and you can just get rid of it over here. Okay, so what we want to do is we want to, what this currently does is, first what it does is, hey, it detects that this has gone off the screen. And immediately what it'll do is, if your frames per second moves it, there's a chance where this could go outside of the screen and kind of get stuck. So immediately what I do is I reset it. I reset the location of the object so that it is before the end of the screen. So I just take it and move it back. That's what this code does right here. But here, after I take it back, I want to modify the velocity. I want to make sure that it goes in a different direction. But since I'm only detecting the x value, I only want to modify the x velocity here, because I only want to change its direction going in the x direction, because I've detected that it's going off to the screen for the x position. There's also an x position change for less than 0, and that's going off to the left-hand side. And that works with y in both directions too. So here we're going to modify the velocity. And what we're going to do is we're going to say that this dot acceleration dot x equals this dot acceleration dot x times -1. Okay, so let's save that and test it. Yeah, well, I'll use keyboard. Okay, so it's stuck. So there may be some issues there. Didn't quite bounce back. We'll play with that in a little bit. First, we got to debug it and see if this is happening. Okay. Actually, no, I'm sorry. It's velocity. I'm doing acceleration, of course. Acceleration changes velocity. Velocity changes location. Remember that. Do it as a mantra. Acceleration changes velocity. Velocity changes location. Acceleration changes direction. Direction changes location. Well, acceleration could change direction or magnify direction. Okay, I'm going to shut up now. Velocity. Okay, so let me show you real quick in the update function. We see, and we got a limiter here, but this is all stuff that we're going to be learning about as we progress. But you see here that we changed the velocity by adding the acceleration, and we changed the location by adding the velocity. Just what I just showed you on how to add vectors. So what we're going to do here is the velocity is going to change the location every frame. So when we change the x and we subtract, or we change its sign to a negative or a positive value, it's going to just start going in the opposite direction. So the update function actually does the addition. So all we have to do for the update function, is we got to check to see, hey, check or bounce our edges. That's function, and when that function runs, the bounce edges function runs. We're going to take the velocity and multiply it by -1 so it changes directions. Woohoo! We got a bouncing ball. Okay. So now all we got to do is we got to go through and do this for all of it. For when... Okay, now this one, it changes a little bit here. It's going to be for Y. All right. So remember, you got to change that in the code that I gave you up here in your update. You've got to, instead of check edges, you got to do bounce edges. Cool. Now let's move around with the keys. Woo! Okay, so you can modify it. You can change its direction with your key. So you've got kind of, hey, if you really want to, this is a good platform to maybe start a game on. But the only problem is most of the code you won't understand until the end of the quarter, which is when we get done with vectors. Or well, actually, no, you got, you'll learn about vectors and forces that are being applied here, towards the almost a couple weeks before the end of the quarter. So I would just stick with your sprite code for your project, the sprite that you got working. And remember, if you've got to bounce edges, if you're able to implement that for your sprite, then you've got your collision detection. Now, another thing that I want to point out is that sometimes you have to optimize your collision detection so that you do what's called a peek ahead. And that's only for stopping little issues where you get stuck in a corner or something. The way that I fix that is in two ways. First, when I detect a collision, I reset the location of the object. The location of the object needs to be reset to a position that's before the detection of the collision for the screen. I then immediately change the velocity to go in the opposite direction of the detected collision with the side of the screen. So another thing that you may need to add in here is to also look at the velocity, plus the velocity. That would optimize it a little bit more and make it better performing, so that you can take into account that if your sprite is going very, very fast, there are points where collision detection fails for some of the. In any case, sometimes you've got to add or keep in mind the velocity of your object when you're fabricating these if statements. Okay, this is actually done for your pleasure. You can use this as an example as you're progressing through the next half of the course. This is some heavy lifting that we're going to be learning, but by the time you're done, you should kind of understand everything that's going on in here. It's also something that you can use as some examples for your own code, such as the bounce edges function and the check edges function. That you can implement in your own code. It doesn't have to be location.x. It could just be, x and y that you use. So you can always implement this code in some form. But one thing I want to point out is the collision detection for the sprite is not done in game.js. The collision detection for all objects should be done inside of the object. So the only thing that we do is we draw the object, we update the object, and we make sure that the object has information about its environment, such as the key state, the frames per second. Also, the object needs to know, when we instantiate the object, it needs to know the canvas width and height. Those are all key to that object being successful. So when we go back to our PowerPoint and we think about our sprite object, we see that this parent width and parent height are very important, especially when you're detecting if your sprite is going off the screen. Okay, so here is some other things that you can do for the challenge. Or actually, nope. Challenge assignment, complete and implement the bounce edges function is your assignment. So we just completed that in the video. One thing that I want to leave this video with is kind of a last quote on vectors by our Nature of Code author Daniel Schiffman, who is did it really well. Most people don't teach this stuff. You can't really learn the understanding of this stuff from books. Really, they got good. 2D game programmers are not going to release their secrets. They're going to be holding on to every bit of knowledge they have, because that's what makes them money. So you got good programmers, you got good authors, you got good game programmers. You do not have good game programming authors. It's just not possible, because they're making more money writing games. One way to think of a vector is the difference between 2 points. Consider how you might go about providing instructions to walk from one point to another. And my answer is through slices of time. You have a direction per time span. And for us, slices in time are up to our awareness, which happens to be 60 frames a second. So I'm sure that we operate on different levels sometime of that 60 frames per second. But that's what a vector is. Direction or location, and direction per time or per frame. All right, guys, go ahead and turn in screenshots of that as your assignment. We did it together. There's going to be a lot of the ones coming up that we're going to do together, especially for this higher level stuff. Remember, this is a class that is built for you to understand how to design a game. You cannot design a game or know how to design a game until you build one. And these are the most common components. And another thing, even though you're working in JavaScript, all this technology is the same. So you can take it to any platform and use the knowledge that you put into understanding vectors and how they work. It goes directly and is applied directly to 3D vectors, which is X, Y, and Z. Instead of just X and Y, they got another. Actually, 3D is 4D programming. 2D is 3D programming. Because 2D, you need your X and Y, but also time. That's your frames per second. So you may, but we call it 2D and 3D respectively, and time is implied. So vectors are that expression of the time portion that describes movement over a period of time. All right, I hope I did it justice and you've got a good introduction to vectors and a little bit of some fun code to play with. Tear it apart. Don't freak out. A lot of this stuff is going to come to you as we progress. This is just a super ultra extremely complicated example that we get to have fun and play with. So go ahead and turn in your screenshot of the code that you adjusted and got working through this video. And then I have some project instructions for you to complete as well for your assignment. Thank you.